All right, everybody, let's go ahead and get started. Thank you very much for joining us today. My name is Kevin Jameson. I'm president at PureAir Filtration, and today we're going to go over some basics of biological air purification or biological odor control. So I am sharing my screen. Hopefully you can see the presentation entitled A Review of Biological Technology for Odor and Emission Control. So this is kind of biological odor control for beginners. Thanks for joining us, and I'll go ahead and get started. Let me get my laser pointer on. So again, thanks for joining us. So I just want to mention to you that PureAir Filtration works in 4 areas in regard to gas and odor control. The area that we're going to be focusing on is in this sector of our business, the odor and environmental emission control. I'll just mention to you that we also work in protecting mission critical electronics from hardware failure, indoor air quality, and emergency gas scrubbers. But today we're focused on emission control. So what are the advantages of biological odor control? So there's lots of different odor control systems out there. There's activated carbon systems, engineered adsorbent systems, wet scrubbers, lots of different types of systems. So what's the advantage of biological odor control? Well, typically, biological odor control has a lower operating cost compared to some other technologies. That's based on the cost based on cost of removal of the mass of odor. So if you take a look at the cost per pound or cost per kilo of odor removed, biological odor control can be fairly significant improvement over other technologies when taking a look at those costs with it. There can be a footprint savings compared to some other technologies with it. There can handle this technology can handle removal of high levels of gases, and that's typically where PureAir trusts this technology is, and those applications which have very, very high levels of gases. And it typically can focus on specific gases. So I mentioned this to you, there's a lot of cans and maybes here because there are lots and lots of options in the area of biological odor control and different ways to approach it. And so it just depends on what you're taking a look at when making those calculations. So let's talk about what this process is that we're reviewing here. How does a biological system work on taking odors out of the system? I think that most everybody understands how maybe a chemical scrubber works, on where you're just reacting with gases that are in the air and turning it into something else. People probably understand fairly well about activated carbon systems and engineered adsorbent systems, where they capture the odor and the odor gets captured inside of the adsorbent. But how does a biological system work? Well, typically these biological systems use naturally occurring bacteria that eat the odor as a food source. So of course, in the world, there's many, many, many different types of bacteria, and there's bacteria that's found at the bottom of the ocean. There's bacteria that's found in the Arctic. There's bacteria that's found even in the bubbling pools of geysers. And when you take a look at all these different bacteria, there are some bacteria that happen to have a great benefit to consume some of the nuisance gases which we find. And so very often these bacteria are naturally occurring in everyday life. A specific type of bacteria that's very often, probably primarily used in the odor control market is an acidophilus or acid-loving bacteria, and that's used for hydrogen sulfide removal. So acidophilus bacteria means acid-loving. It means they like to eat hydrogen sulfide. There are other bacteria and even some fungus which are used to take out volatile organics and ammonia. It's very seldom, though, that you'll see a system that could take out all 3 of these. It would be a very complex system. and it might not do a great job for any of those if it tried to focus on it. So typically these biological systems are focused on removal of one kind of family of odors. As I mentioned before, the odor is the food for the bacteria, and a lack of odor can cause a microbial failure. So bacteria will die if they're not fed very well. So keep that in mind when you're looking at bacterial systems, is you have to have enough odor and odor consistently coming through the system in order to feed the biological system. So if you have an application that sometimes has odor and sometimes doesn't, it might not be a good application for biological. Or if sometimes the odor level goes very, very low for a period of time, or if you have to shut the system down for extended periods of time, then that may not be a good application for a biological system. A biological system is typically best when there is a significant odor level and it runs at a consistent level. That odor does. In biological systems, if the media, which is in the system that's used as the substrate for growing the organic matter, if that media is organic, and we'll talk about that here shortly, then the bacteria typically get their nutrients from this. So when I say nutrients, we're talking about basically vitamins and minerals that we would think about. So the bacteria gets their kind of energy source from the odor that they eat, but then they get their vitamins and minerals from this organic matter. If you're using an inorganic medium, and we're going to talk about this medium coming up as well, you'll need to supplement the system with some nutrients as well. So basically a little bit of fertilizer in the system to keep those microbes healthy. Certain bacteria have to also be kept at very specific pH levels. So for instance, this acidophilus, acid-loving bacteria, wants to only live in very acidic environments. So for instance, those environments that I mentioned in geysers and such where they live are very acidic, and the bacteria like it that way, and you have to keep it in that level for those bacteria to function very well. So it's very, very common, or it's typical that these biological systems have very, very low or very acidic pH levels there. Also keep in mind, bacteria grow within a certain range of temperature. So they require a source of foul air for food. They need water and replenishment water because they are basically waterborne microbes, or at least need a great deal of water to live. But also keep in mind that temperature typically has to be what we would kind of refer to as ambient. You can't get to a freezing level and you can't get too hot. These bacteria are typically operating at a mid-range temperature, which is typically fine for odor control, but you have to keep in mind if your installation is in an area which gets very cold in the wintertime or very, very hot in the summertime, that those things need to be considered, that they could have an adverse effect on the operation of the system. Also, keep in mind, all biological systems require an extensive startup period to colonize the microbes. So you don't just start off on day one with a full colony of microbes to do all the work. You have to start with a little bit of bacteria and you have to feed them, and then they grow, and more bacteria grow and grow and grow, and you end up building up the colony size that you want. And that colony size will grow to the size needed based on the amount of food coming into it. But that often takes at least a couple of weeks to build that bacterial load in the system up. So just keep in mind with that system that it's not simply a turn the system on and it operates. So let's talk. So I mentioned to you before about the various microbes that are available for odor control. So here are some of the known microbes that are used commonly in the industry. So I'll just give that to you as far as, some of them are fungus, most are bacteria. As far as they go, some are aerobic, some are anaerobic, etc. And there's also various pH levels. So of course you can target for a specific bacteria, and that's typically what we do with our systems with it. And so there's an optimal and kind of a maximum, a min pH level for each of these to work in. So probably one of the more confusing parts about the biological odor control industry is the terminology, the naming of these and the definition of these biological systems. The first point that I'll make is there is no standardization in the industry for these at all. Talking from one manufacturer or one industry expert, one consultant, to another, there is absolutely no standardization. So the term biofilter, bioscrubber, biotrickling filter, biotower, bio something means a little bit different to just about everybody. But generally, for the terms of what we're going to discuss today, we're going to break these systems into two categories. Basically, a biofilter and a bioscrubber. So a biofilter is generally has an organic substrate. Generally, there's some exceptions which allow for desired bacterial growth, and air is percolated up through the system. So this is typically a fairly basic system. We'll go into details on it in just a moment. A bioscrubber is a system with a high surface area, typically inert substrate, which pumps nutrients and water through the substrate, typically in a recirculating mode, and promotes that bacterial growth. So it's somewhat more of a, I wouldn't want to call a biofilter not an engineered system, but let's say a bioscrubber is a more engineered system. It's a more complex with pumps and typically instrumentation and meters and such, but typically has a higher performance level. So a higher engineered level, a higher performance level. This is typically also the system that would be referred to as a biotrickling filter. Unfortunately, biotrickling filter is also a terminology that's used in water purification as well. So that creates some confusion. But biotowers, biotrickling filters, bioscrubbers, those are generally the same type of system. So here's a biofilter. Here's an example of a biofilter. Okay, these are typically fairly simple systems and generally fairly effective. In general, you have an intake for your odor where a blower blows air into a humidifier. So one point about a biofilter is the microbes, this entire process requires a very high humidity level, typically 99% humidity to being pumped into the system. Once this humidified air comes, it blows into the bottom of a system. Typically, there's some type of air distribution channel that maybe there's some piping and such in the bottom that's covered with a gravel. All right, and then on top of that gravel is a filter medium. So here you can see an example where a structure has been created. There is a blower here. It's blowing into a humidifier. This humidifier is creating this high humidity air. That air is being pumped into the bottom and it's percolating up through this biomedium. And we're going to talk about this filter medium in just a second, but that's how it is. It's typically in the open. This type of an application you see here is very good for areas of the world which have fairly tolerable temperatures. Obviously, if this type of a system, this type of above ground kind of thin walled system were installed in a extremely cold environment, that cold would get into the system and would probably affect that system. So this would not necessarily be the best. This is also open, so it's open to rainwater, which can be a concern for the systems. And if you're in an extremely wet area of the world, that might be one consideration that you have to be concerned about, is getting it too wet with that and having to worry about the drainage of the system with it. And of course, too hot or too cold are certainly factors for a system like this. So how does this biological system work? So I mentioned to you, foul air is ducted in through a blower. The bacteria grows on this filter medium. The bacteria use the medium for nutrients, as I mentioned before. So this filter medium is something that the bacteria can live on and then also consume to some degree. Hydrogen sulfide, which is the primary odor used for this traditional biofilters, is the traditional odor where that most biofilters use. This hydrogen sulfide is oxidized by the bacteria, and just generally that the amount of contact time that the air needs inside of this filter media is typically about 30 seconds. So that varies just depending on the type of filter media you're using, but the general rule of thumb in the design world for biofilters is to need about 30 seconds of contact time for the air to be in this filter media as it percolates up for about 30 seconds. So a biofilter is very simple. There's not a whole lot of parts. There's only one moving part, that's the blower. The humidifier is a fairly simple piece. There's some drains and such, which all kind of work on their own with that. So it's not very complicated. It's typically good for fairly low levels of odors. Biofilter might not be used for extreme high levels of odors, typically lower levels of odors. And it's generally fairly, because it's fairly simple, it's fairly low maintenance. I'll mention that there are issues sometimes with the filter media compacting in areas. Occasionally, there is some maintenance required to go through the filter media and fluff it back up. You do have to make sure it stays wetted. Sometimes some systems have a sprinkler on them in order to keep, even though the humidity coming up the system should be enough, sometimes there needs to be a little additional wetting on there, but in general, they're fairly low maintenance systems. So this is an example of a schematic and a photo of a bioscrubber or the biotrickling filter, biotower type system that I mentioned prior. So this is more of an engineered system. You can see that this has been a fabricated system. Typically, odors are brought into the system. VOCs or hydrogen sulfide are typical applications. They're brought into the bottom of the system into this plenum section, and the air is pushed up through a substrate, a medium which is growing the bacteria, the microorganism. This is typically a non-organic substrate. It's some type of inert porous substrate that gives the surface area of the bacteria to grow on. So you need a lot of surface area. The key with all biological technology is the more surface area you have, the more effective the system is. There's a spray system on top so that there's water with nutrient, which is sprayed down. It trickles down through the packing in the system. Any excess water comes back out and is either drained or recirculated in the system. You're typically putting fresh water into the system to make up for the contaminants that have been brought into the drain of the system. So discharged air basically is coming out without any of the odor involved with it, whether you're taking out VOCs or H2S or ammonia, whichever you're looking to take out. So taking a look at this just a little different as some of the different components of the system. So foul air is ducted into the tower, typically in the bottom. Media grows into this section where the gas is oxidized. The water is a nutrient is recirculated, and we're typically going to see somewhat 90 to 95 or 95 to 99% removal. So these systems are a bit more complicated. You've got pumps and sensors and valves and makeup waters and nutrient feeding into the system. They're not extremely complicated, but there's certainly a higher level of engineering involved with it. These systems are typically effective for very high levels of odors, applications of even thousands of ppm of hydrogen sulfide. We've seen applications for. Those are typically very, very stringent requirements on a system to have that high of a level of odor. And the maintenance level we would say on these systems is typically what we would say medium. they don't require necessarily daily attendance to them. But if the system's gonna perform well, it does require some good maintenance of the system. So that's just something to be aware of. It's not simply a system that can just be turned on and walked away from for an extended period of time. So here's examples of biofilters. Going back to biofilters, here's an example of biofilters. So biofilters can be either in ground. Here's an example of a very simple in-ground filter. Look, the customer has just simply dug a hole in the ground. He's laid some pipes for air distribution. He's covering it with gravel, and then he's going to, on top of this gravel, he's going to probably put down some mulch or some bark or something in there as well. So this is very, very simple, very low cost. You just need to dig a hole and put some gravel and pipe and bark in it. And to some extent, you've got a biofilter working to that point. Now, is the performance of this system going to be, extremely high? Maybe, maybe not, but this very well could serve as an excellent odor control for the need of this particular customer in this particular case. So this would be an in-ground. Here's a couple examples of above ground systems. Of course, in-ground systems are helpful in colder environments because you get the ground temperature keeping everything warm and insulated with that. So that can be helpful in a cold weather environment. These installations are not in cold weather environments. They are above ground. And even though this is a biofilter here, followed by an absorber polishing system, but obviously this is concrete, and cold can get through concrete. And so that's a concern that might have to be addressed in this case. This system, I happen to know, is in a moderate temperate climate. And so while it might get a little cold in the wintertime, it's probably not cold enough to greatly affect the performance of the system. And here you can see this is a poured in place concrete above ground system. This system is a engineered system. So it's a built at the factory, let's say, system that's dropped in place above ground type system as well. So lots of options to work with. This is a covered system as well, because the odor, any remaining odor that might be after the biofilter, the odors, the outlet of the biofilter is here. So that air is then being expelled into a polishing system to capture any possible odors that might have gotten out of the biofilter. So this system is not a covered system, and so the odors are just simply coming out there. And obviously this outside system is probably not going to be a covered system as well. So for a biofilter, what is the medium that goes into a biofilter? Well, interestingly, there's lots of different options, and of course lots of people have different opinions about what option is best, but generally porous organic matter typically works fairly well. So mulch, bark, wood chips, these typically work fairly well. Bacteria can find a home inside of these. They typically hold moisture well and have a good surface area for the bacteria. They're also very low in cost there. Coconut husks can also be used. Coconut husks are very nice in that they have a nice structure to them and certainly have a lot of surface area to it. With that, sometimes even just plain soil can be used, especially if it's a soil that doesn't compact very much. You wouldn't want to use a clay, but you could certainly use kind of a heavy organic soil as well. Peat could very much be used. Peat has a high organic content, and so we get that high organic content to provide nutrients to the bacteria. So peat can also be used. And I'll also mention that engineered products can be used as well. This is a glass foam product, so it's made from recycled glass. It's a very, very porous product, has activated carbon built into it as well to have that carbon base for nutrients for the biological to have a nutrient to get nutrients from. So that's biofilter medium. So let's take a look at Bioscrubber Medium. So these are typically engineered systems, as I mentioned. So some of the original Bioscrubber Medium were actually lava rock. So lava rock, this is typically a highly porous rock with it. And that was some of the first bioscrubber mediums that were used. And a lot of great bioscrubber installations were done with lava rock. Probably the biggest problem with lava rock is that it's very, very, very heavy. So from a structural standpoint, that lava rock typically has a really just a huge high density to it. That lava rock becomes problematic just from a structural standpoint, from a transportation standpoint and such. But lava rock was used. Also, pawls are used. This is basically a wet, the same type of material you would use in a wet scrubber packing you could use. And these are synthetic, typically made of some type of a plastic, and they provide some surface area with these various shapes and such that they have. Also, some urethane foam has been used, these foam cubes. These are kind of porous, semi-rigid foam cubes. There's also some polyester mesh roll type material that can be used in these towers. And then that glass foam that I mentioned to you before, doesn't require the carbon substrate on there in a bioscrubber. This is what we utilize. This is our self-absorb SI. So very, very light. It's probably 10 times lighter than lava rock, extremely light, and maybe even more, even less than 10 times as heavy as lava rock, and far, far more porous. This is extremely porous product. And the key with bioscrubber technology is surface area or porosity. The porosity creates the surface area. And so this extremely porous glass foam can be used to really create a huge amount of surface area to provide that surface for the biological reaction to occur. So let's discuss bioscrubbers. So, typically it can be stated that a bioscrubber is 99% plus removal efficiency of, for instance, hydrogen sulfide, typical application. That's very, PureAir can claim that all the time if the system is monitored closely. What we typically see is at startup, sure, the system is running at 99%. Typical operations, unless the customer is really staying on top of the system, the reliability is probably more like 95% under, let's just call it basic minimal operation from that. So the customer can operate it with a higher level of attention at 99%, but we would probably say a more realistic value is about 90% removal efficiency. Well, keep in mind though, that if you've got 1,000 ppm, even 99% removal is going to leave you with 10 parts per million of H2S remaining. 95 is going to leave you with 50 parts per million left over. So that's a very, very high level. So we just need to keep that in mind, that these systems typically operate under high levels of gas and give high efficiency levels, but that doesn't mean that they take every bit of the odor out. Bioscrubbers are typically designed for colonization of one type of bacteria. There are some systems which have layers of bacteria for various layers of odor, but typically the highest performance systems are typically colonizing one type of bacteria to take out one type of odor. Typically, in this case, maybe hydrogen sulfide. We'd use an acidophilus bacteria in order to focus on hydrogen sulfide and do a great job of removing hydrogen sulfide. If other odors came into the system, they might not be removed with such high efficiency as the hydrogen sulfide might be. Bioscrubbers, these systems this bacteria naturally creates a low pH bed. So keep in mind, inside of the bioscrubber, the pH of the liquid is going to be about 1.5 to 3 pH, very, very acidic. that is where you want to be with the Bioscrubber with it. And so we try to maintain that level with the Bioscrubber. If we get below 1.5, that's when we start draining off some of the liquid in the system and adding fresh water with that. In H2, in the biological process for H2S, the leftover products after going through the digestion of hydrogen sulfide or elemental sulfur and some sulfates, these can typically be washed out. So the system's just under continuous operation, washing out that material. For these systems, because they're more engineered and have higher surface area and higher efficiencies, typically your empty bed residence time of 10 to 15 seconds is all that's needed. So typically about half to a third of the residence time is required for a bioscrubber compared to a biofilter. And that's the advantage of having that engineered system. Do keep in mind that these systems typically require a constant water recirculation or introduction into the system. So you've got to have some kind of water source coming to the system. And as I mentioned before, supplemental nutrients are required to keep the bacteria healthy. But if you have secondary influent coming into the system, you can, if you're at a wastewater treatment plant and can use some treated water to go into the system, the nutrients in that can be used instead of adding supplemental nutrients. So that can be a real beneficial at a facility, at a wastewater treatment facility. You can use your influent there as a source of nutrients. So let's take a look at some of the advantages and disadvantages of bioscrubbers. So typically the operating costs are far lower than a chemical scrubber. So a chemical scrubber simply takes one chemical and interacts and neutralizes the gas that you're wanting to remove with it. So typically the operating costs are much, much lower for a biological scrubber compared to a chemical scrubber, because you're using the bacteria for making the reaction and making the oxidation of the gas. Typically, you're only dealing with about 3 inches of water column in the design. The packing inside the system is not a very high pressure drop, so you don't have to have really high pressure fans. Typically, H2S and ammonia are typical applications for a bioscrubber. Some work has been done with VOCs with bioscrubbers, but the typical application is hydrogen sulfide or sometimes ammonia, but typically hydrogen sulfide. I mentioned to you, 99% removal efficiency is very possible with good attention to the systems. And generally there's no chemicals required. There is some nutrient, I guess you would call that a chemical, but that's basically a mild fertilizer, unless you don't even need that as long as you've got treated water to put into the system. Some of the disadvantages, you've got to have that constant food supply. All right. So again, if you have odors that are intermittent, if they're part of the year but not part of the rest of the year, if the system has to be shut down for extensive periods of time for some reason, this is not a good technology. This is for continuous operation at consistent levels of odor. You've got to have that water source I mentioned, the media bed where the bacteria are growing, the microbes are growing. It has to be in that 50 to 100 degree Fahrenheit range. We're working on an application now in a cold weather environment where we're having to concern ourselves with the air coming into the system being very, very cold and potentially harming the bacteria. So we're actually having to add heaters into the system to keep the fluid warm, to keep the bacteria in a good zone for operation. Keep in mind that you're also going to have a low pH drain water. So that low pH drain water in that 1 to 1.5 to 3 pH has got to be handled properly according to your local regulations. That how are you planning on handling that low pH water which is draining into the system? So there's various ways of taking a look at that, but that's just something that you need to be aware of there. If you're at the wastewater treatment plant, that's not a problem, but that's something that does need to be considered. And do keep in mind that typically these systems are not designed for total odor removal. They're designed for focus on a particular gas. They can remove some other odors, but they're typically not focused on removal of a broad range of odors. So I'll mention to you as well, one of the areas that we focus on in promoting the technology at our customer is multi-stage systems. So here's a couple of examples of multi-stage systems. We saw this system before. This is a biofilter. It's a covered biofilter where we're taking the air after the biofilter and we're feeding it into a couple of absorber units. So this could be activated carbon, though activated carbon is not the best product for after a biofilter. The reason for that is the air is extremely humid, and activated carbon itself doesn't work very well in a high humidity environment. But there are other engineered adsorbents that do work very, very well in these applications, work in that high humidity environment. And so this polishing system might be used to either pick up any residual hydrogen sulfide that's left over from the biofilter, or to pick up those other odors that are there. Same thing with the bioscrubber. So here's engineering illustration of a bioscrubber. So this is your tower. The odors are the outlet of the system is coming out. Any residual odors are being brought into this this engineered adsorbent system, where any residual odors are being captured there. So what's the benefits of these hybrid biological/adsorbent multi-stage systems? So we call those a hybrid system because they're using two technologies in one type of a system. Advantage, the adsorber system after the biological system captures those other odors. I discussed that earlier. Just captures those other odors that are maybe not the focus of the biological system. So for instance, mercaptans and dimethyl disulfide, those are probably not going to be removed very easily by a biological scrubber, but an adsorber system afterwards would pick up those residual other odors that can be available, that are almost always in wastewater treatment odor control. Adsorber systems capture odors not captured in biological systems during peak periods. So let's say that your biological scrubber is designed to operate at 200 parts per million, but occasionally you get a surge of 300 ppm into the system. Well, the biological system, which normally operates at 200 parts per million, can't react quickly enough to build up the bacteria needed to handle 300 parts per million. So you're going to get a surge through the system. And so the adsorber system, that should be a D right there, the adsorber system is there to pick up that peak, to shave that peak. Adsorbers serve to provide odor control while the new biological system is starting up. Remember, I mentioned there that we've got kind of a 2-week period where the biological system is growing, the biological mass are there. So that adsorber during that startup period acts as a crutch to help it along, to make sure that you're not spewing out odors into the area while the biological system is starting up. It also provides that same function in the case of an interruption. So let's say that there's a breakdown of some system in the biological system. Maybe the recirculation pump has failed and the biological mass has become hindered by it, that there's some type of interruption of the biological system. Then the adsorber serves as a backup while the biological system is brought back up to operational mode. Also, adsorbers capture odors that are generated by the biological mass. So keep in mind, it's bacteria, and bacteria, while it's capturing some odor, can also have its own odor, a little bit, kind of a musty smell in most cases. And so the adsorber can capture those musty smells. So typically, a multi-stage hybrid system is going to take a lot of odor, and out of it is going to come completely purified air, which is absent of any kind of odor While as a biological system, it's probably not going to be completely absent of odor. It's probably going to have a low level of odor coming out of it most of the time with it. So anyway, that is our presentation on biological systems, and I thought I would open it up at the moment for any types of questions. There is a Q&A portion at the bottom of your screen. If you'd like to type in some questions there, we'd be happy to answer any kind of questions that you might have. So I'm not seeing any questions. I don't know if I have answered everybody's questions in my presentation, but I certainly do appreciate everybody's time. We'll give it another minute or so to see if any questions do pop up. But if not, we certainly appreciate all of your time. Certainly, this is going to be recorded and available on our YouTube channel. So we will send out a link to you to let you know how to watch that video in case you want to forward it to somebody in the industry to look, or just to go back and take a look at points. And of course, you're always welcome to send us any questions. You can reach us in general at info@pureairfiltration.com, or go to the website pureairfiltration.com. And of course, you can reach me personally, K. Jameson, at pureairfiltration.com, KJAMESON